Hello everyone, welcome back in the course on higher surveying, and we are in module 4, error, accuracy and adjustments computations. In the last lecture, we have seen the observation equation method for adjustment computations, and then we talked about how to find out the MPV, which is equal to the mean for given observations, and then we have solved many examples, multi-response example, single response example, and then we have seen that how to construct the weight matrix. Today we are going to learn a nonlinear example of observation equation method. We are also going to consider how to construct the weight matrix and what is a cofactor matrix. Secondly, we are going to see what is the condition equation method, which is quite different from observation equation method. So let us start here. So we have discussed that the weight matrix P, that is written as W1, W2 and all the diagonal elements valid, and all other off diagonal elements are 0. So, I write big 0 here and big 0 here, because all these observations x1, x2, xn are coming from field observation. Okay. Then we have said that we have devised and the Wi is equal to sigma 0 square divided by sigma I square, where sigma 0 square is reference variance or variance of unit weight, right. We have assumed this value, and also this value is coming from either experience or in general it is coming from the specifications of the instruments. So, I am using the specifications of instruments to estimate this sigma I square. So, it is general idea that we are using some instrument for measurements. So, instrument should give me this kind of quality in the observation, even if I take one observation. Okay. After discussing this thing, now if I consider the matrix sigma LB LB, which is nothing but sigma x1 square, sigma x2 square and sigma xn square. It can be any variable, I am just, and all the rest of the elements are here, fine. So, can I derive matrix P from this matrix? So, let us look into another matrix called QLBLB, that is called cofactor matrix, and it is defined as sigma LB divided by sigma 0 square, like this. So, I am dividing the each and every element of sigma LB by a constant value sigma 0 square here, and as a result what will I get? I will get a P matrix as an inverse of QLB. You can see here. And so on. Zero, and here off diagonal matrix elements are 0 here. So, you can see here, if I construct the QLBLB this form, and if I take the inverse of QLBLB, which is cofactor matrix here, I can find out the weight matrix of given observations, which I measured in the field. And remember, in case of observation equation method, we say that the QLBLB or the sigma LBLB is explaining or describing the quality of dependent variable. Moreover, independent variable is always errorless. That is the assumption we make in the observation equation method. Now, here if you see carefully that by taking this ratio, I have elevated two problems. The first problem, which was the minor problem was the numerical error. That means, if I take the observations in centimeter or meter, then the value of this sigma I will be in different units. And as a result, if I take this ratio, it will happen that the ratio will be removing the factor of units. And so, even someone takes centimeter or someone take the meters unit, does not matter. Secondly, I have derived a major advantage here. The major advantage is, by taking this ratio, I need not to consider sigma I square, because sigma 0 square is a reference variance for unit weight, and as a result, if I take the ratio of these two, I can find out what is the weight of observation. For example, if I say observation number 1 is 1.5 times better than some other observation. So, I can say this observation, which is other observation, it is having unit weight 1, then this observation should have a weight of 1.5 because it is 1.5 times better than this. So, it is 1, then it is 1.5. That is the idea, and that I can establish with the help of taking this ratio. Okay. So, let us take an example here of observation equation method. I want to do the georeferencing x cos theta plus y sin theta plus let us say T x, that is first equation. Second is minus x sin theta plus y cos theta plus T y. Here T x and T y are the translation in the capital X and capital Y, such that I will get these two equations here like this. It is very simple equation of the translation and rotation, that is conformal transformation about z axis by theta angle and then translation. Suppose if I have a map here, or maybe I can say there is one image and I am trying to bring another image into that, or I am trying to rotate this image by angle theta in the some coordinate system. Let us say this, I want to rotate this image by this angle like this, and this angle is let us say theta, fine, and I want to shift this origin of this one, which is T x T y, right. So, that is the equation I have written. As per the standard process, what do? We introduce this error V x equal to similarly y plus V y equal to x sin theta plus y cos theta plus T y. If I try to find out V x and V y for n number of observation, they will be like this: V x 1, V y 1, the small v's, okay, and so on. I can write V x nth observation or V y nth observation like that. So, and then here what will happen? I can write matrices as x 1, y 1, 1 here, and then I can write here, let us say plus y 1 minus x 1, 0, here 0 and here 1. Well, try to write yourself, I am not writing all the things. X n, y n, 1, 0, y n minus x n, 0, 1, and here unknown parameters cos theta, sin theta, T x, T y. Try to check whether you are getting n number of equations which are written by repeating these. So, this is the matrix arrangement. Then finally, L matrix, which is given by x 1, y 1, x 2, y 2, x n, y n. I can call this as L matrix here. This is parameter matrix capital X. This is A matrix here, and this is V matrix here. And now you can use X equals to A T A inverse A T L, or I can also use weight matrix P if I assume in this case P is equal to identity matrix, and here it is not an identity matrix. So, I am writing this thing. So, that is the idea. If you observe X, what is this X? This is matrix cos theta, sin theta, T x and T y. So, basically what I have done here, I have assumed cos theta and sin theta as parameter A and B. Similarly, so I am writing here A and B. So, then I have 4 parameters 1, 2, 3, 4, but I have not determined theta. Theta I have to determine again after finding out A B, then I will be writing tangent theta will be B upon A, and then I will be saying theta equals to tan inverse B upon A, right. So, what about the quality of the theta? That means, if I find out sigma xx, so I will be finding out here sigma A square and not the quality of theta, it will be quality of cos theta. And that is the problem with linear approach when there are some non-linear functions like cos theta, sin theta. How to deal with such situation? Once again, write the same set of equations, and here I am writing, let us say, x cos theta plus y sin theta plus Tx, y equal to minus x sin theta plus y cos theta plus Ty. Capital X is f of, let us say, theta, Tx and Ty, let us say f x, and similarly y equal to f y is equal to function of theta, Tx, Ty. Now, instead of using a linear approach where I linearize my parameters, I will linearize my function f. What does it mean? Use the Taylor series and write it approximately as, let us say, x0 value, which is the initial value here, then dot f x divided by dot theta into delta theta, that is first order approximation by Taylor series, dou f by dou Tx into delta Tx, and here again I am writing dou f x by dou T y delta T y. So, what about these values? These values are evaluated at x equal to x0, some known values of the parameters. This is what we do in a standard Taylor series. We write about, and we are ignoring the other higher order term. Right. Similarly, I can write y equals to y0 plus dou f y by dou theta 0 plus dou f y by dou T x into delta T x. Again, it is evaluated at some value of y equal to y0 and x equal to s0, right. And here dou f by dou T y into delta T y, yeah, and we are ignoring rest of the terms. Again, evaluated at y equal to y0 and x equal to x0. Now, this is linearized form. Okay, I introduced the error Vx and Vy at this stage. As a result, I can write this as Vx plus this one, Vy plus this one is equal to this one. That means I am writing the adjusted value of the dependent variables now here, and I can form the v equal to Ax minus L, where if I write this thing, what will happen? Vx, Vy, if I write just for one observation, it will be Fy here, it is Fx here. Right. So, let me write this form in this way. Yet dou f by dou theta by dou Tx dou f y by dou T y into, I can say, delta theta delta Tx delta Ty minus x minus fx0 and y minus x fy y0 here like this. I can also write these values x0 y0. Okay, so this is for one observation. Now this is matrix A, this is matrix unknown X, this is matrix L, and this is matrix V. So this is the form V equal to Ax minus L. Rather, I write instead of x, I have now delta x, which is the corrections to the assumed value x0, y0. Okay, so let us write this thing as x equals to function fx of theta tx ty, or I can write here x cos theta plus y sin theta plus tx. Y equals to fy of theta tx ty, which is nothing but minus x sin theta plus y cos theta plus ty. Okay. So that was the example where I said that, okay, let us see, I am observing x1 y1 corresponding to x1 y1. It could be datum transformation, it could be a two-dimensional transformation of the two images or two data set, anything. So now I am observing like this, x2 y2, which is corresponding to x2 y2, and so on, xn yn corresponding to xn yn, and I want to bring this transformation. So my unknowns are theta, tx and ty. To use the Taylor series, x by Taylor series expansion, that means fx, I am evaluating it at theta 0, tx 0, ty 0, some known value, plus dou fx by dou tx into delta tx plus dou fx by dou ty into delta ty. That is first equation. Same way I can approximate y by fy theta 0, tx 0, ty 0. So these are initial values. Then again in the same fashion I will write I hope you are trying to write it and you can convince yourself here. Okay. Here I would like to mention that we are ignoring the higher order terms in both fx and fy because we are taking first order approximation. Let us introduce the error in dependent variable x and y. So let us say Vx plus x equals to this expression fx, this I am not writing the full form, and then delta theta plus okay, here let us say theta 0, tx 0, ty 0, right. Similarly, I can write Vy plus y equals to fy theta 0, tx 0, comma ty 0 plus let us construct our V equal to Ax minus L, where let me show you what is the V matrix here. So this is V matrix, dou fx by dou theta, dou fx by dou tx, dou fx by dou ty, dou fy by dou theta, dou fy by dou tx, dou f y by dou t y into delta theta delta t x delta t y. Then we write here x minus f x theta 0 t x 0 t y 0. Y minus f x theta 0 t x 0 t y 0 and so on. So, these are the values of function f here evaluated at theta 0, t x 0, t y 0, which are initial approximation or initial estimate to start calculations. Similarly, I have evaluated Jacobian matrices at the theta 0, t x 0 and t y 0, which are initial approximation. This is V matrix, this is A matrix, this is parameters matrix here, and this is L matrix. I can write for n number of observations like this. So, if I write for unknown number of observations Vx1, Vy1, Vx2, Vy2 and so on Vxn, Vy1, and finally, if I solve it, I will get x equals to At A inverse At L, and if I know the weight matrix P of observations capital X capital Y, I can write weight matrix also here. Now, what is the message here? If you see what is delta x in the last slide, this is delta x. Delta x equals to delta theta delta tx delta t y transpose, which means I am finding out the corrections to the theta 0, tx 0 and ty 0 here. This is first iteration. I will update theta 0 as theta 0 plus delta theta, that is last value assumed. This is my correction which I find out here in this step, and then similarly I will write a new value of tx 0 as earlier value of tx 0 plus the update delta tx. Similarly, ty 0, I will write here ty 0 the previous value and the update. So, by updating or by making these small corrections, I will find out new values, and these are the previous values which I assumed originally. Now, I got the new set of values here. I will use this new set of values, perform the same calculation, where I will use this formula. That means, I will reconstruct A matrix, I reconstruct L matrix, and I will find out delta x again. Again, it will give me some corrections, then again I will update values, which second time I find out. Now, this process will be continuing till corrections become very, very small. That means, there is no improvement in the corrections, there is no update in the theta 0 value, and as a result, whatever theta 0, tx 0 and ty 0 I will get after n number of iterations, I will say that is final answer. And this is the way we handle the nonlinear problems by observation equation method. So, let us go ahead and see there are some situations where I cannot use the observation equation method. If you remember our triangle example, this angle alpha, this is beta, this is gamma. Ideally, I can write alpha plus beta plus gamma, which are adjusted values, equal to 180 degree. So, this is the condition equation. However, we have also said that I am measuring alpha n alpha times or maybe n times whatever, and then I am finding out alpha bar as mean, right, and mean is nothing but I can say here summation I equals to 1 n times or maybe n alpha times alpha I divided by n alpha. Same way I find out beta bar and gamma bar. So, these are coming from observations, and this is ideal relationship. So, here if you see, all the three variables are observed in the field, and there is no dependent variable or independent variable, because I cannot say that alpha is dependent and beta gamma are independent variables, right. Although mathematically I can write like this, alpha equals to 180 minus beta plus gamma, but still there is no point of calling alpha or beta or gamma as a dependent variable. And such a situation, when all the variables are measured, we can solve by condition equation method. So, let us introduce the condition equation method. In case of condition equation method, we measure all the variables. Remember, there is no dependent variable and independent variable in some situations, but we are measuring all the variables. In observation equation method, we can recall that there is a dependent variable which is a response of independent variable physically, and hence we write that explicit equation between the dependent variable as a function of independent variable and parameters. This is not the situation here. All the variables involved in the physical phenomena that we are going to observe are measured. What is the condition equation method? If I write all the adjusted values, let us see if I write alpha A adjusted, beta A plus gamma A should be equal to 180 degree. What's the meaning here? If I say alpha A adjusted value is nothing but alpha bar plus V alpha. Similarly, beta adjusted value is beta bar plus V beta, and similarly the gamma adjusted value is gamma bar plus V gamma. I can write this condition equation as f of LA. LA is nothing but the adjusted values of the variables. That means I am writing alpha A plus beta A plus gamma A minus 180 degree equals to 0, and this is the form of condition equation method here. Right. Let us try to solve this one using matrix method. I am solving it here. The alpha A as alpha bar plus V alpha, beta bar plus V beta plus gamma bar plus V gamma equals to 180 degree. Now, I can write here that V alpha, V beta plus V gamma, which are errors, equals to 180 degree minus alpha bar plus beta bar plus gamma bar. I can write this equation in the form of matrix now as 1 1 1 V alpha, V beta, V gamma minus alpha bar plus beta bar plus gamma bar minus 180 degree equal to 0 plus here, sorry, right. So, this becomes B matrix here, this becomes matrix V here, and this becomes W matrix here, and this we call the mixed closure or W matrix here. So, I am writing the form BV plus W equal to 0 for the condition equation method here. What is unknown? And the unknown here is V, because the moment I know the V, I will add it to the alpha bar, beta bar and gamma bar, and I can find out the adjusted values. That is it. This is what I want. So, here in case of condition equation method, residuals are the unknown, or I can say each variable is unknown, but they are connected with the condition equation, and that is why I am using condition equation for my adjustment process. Before we write the solution, let us first go by the fundamental principle which we said that we want to minimize VTPV. Since I know BV plus W equal to 0, so if I take a multiplier KT according to dimension of BV matrix plus this one, this whole quantity is equal to 0, because this is a scalar quantity, or what we call Lagrange multiplier, and this is already 0. So, I am not adding anything to phi. I can write this thing like that. Okay. Now, I will do the same process of least square solution, where I will differentiate phi with respect to the parameter, that is nothing but in this case V, and I will put it equal to 0. Dou phi by dou V beta, dou phi by dou V gamma equals to 0. I will get 3 equations. Using those 3 equations, I will solve it and I will find solutions, right. I am doing the same thing by matrix method. That means using this only, we can write straight away the solution V. It is also written here P inverse BT, M inverse W. This matrix is also written here M. So, that is the solution. So, we will find out the unknowns here. Let us take the same example of three angles of a triangle. There, can you use this formula to find out the solution? Try yourself and find out that V alpha, V beta, V gamma will be equal to E by 3. What we have find out, or what is E? E is nothing but alpha bar plus beta bar plus gamma bar minus 180 degree, or you can write other way around also. Why? Because it is error could be positive, it could be negative also, no problem, right. So, you should get this answer. Try to solve this V matrix, and what is V matrix? It is nothing but V alpha, V beta, V gamma transpose, or it is a column matrix. So, by putting the values here, and for simplicity you assume that your P matrix is identity, which is nothing but 1 1 1 0 0 0 0 0 0 here, and try to put all the values here, and you should get the correct value here, right. So, that is a homework. Remember, we have said in our original derivation that let us assume that alpha bar is measured n alpha times, and hence it has a weight W alpha. Similarly, beta bar is measured n beta times, so it has a weight W beta, and gamma bar is measured, or gamma I can say, not gamma bar, yeah, gamma is measured n gamma times, so it has weight W gamma. What will happen if I have weight? That means my weight matrix is like this. Well, I have solved BV plus W form. In this BV plus W form, V matrix is nothing but V alpha, V beta, V gamma, and B matrix is 1 1 1 plus W is, we can say, alpha bar plus beta bar plus gamma bar minus 180 degree is equal to 0. Okay. So, now I put the weight matrix here, then what will be the solution of V, which is equal to V alpha, V beta, V gamma is equal to P inverse Bt, B P inverse B T inverse, I am again writing the same formula W here, right, this B matrix here. Okay. You put this and try to find out. I have already found the solution. I am getting V alpha equals to W beta W gamma divided by W alpha W beta plus W beta W gamma plus W alpha W gamma here, and here we have this one, right, and then you get V beta equals to W alpha W gamma into what is the value of V gamma? It is nothing but W alpha W beta divided by again this summation you can see here the denominators in 3 terms is constant, right. Assume that beta and gamma are measured with higher confidence, so they have higher weights. It means that alpha is measured with lower weight, or alpha has more errors because you have low confidence in that. It is reflected here. Why? Because the V alpha, which is error in the angle alpha, it is proportional to W beta and W gamma. That means if beta and gamma are measured with higher confidence, they will have higher weights. Automatically, this will contribute more error to this alpha angle. Similarly, you can see with other angles like what is V beta and V gamma. Automatically, if W alpha is less, it will contribute less error to V beta as well as V gamma. That's the idea here. You can understand that what is the magic of the weight. The moment you assign the weights to the observations, how errors are going to change. Okay, I would like to introduce two terms here. One is condition. You might have come across this time the condition equation, and another term is constraint. Condition is a, I can say, mathematical equation or condition which has to be satisfied. However, under the influence of random errors, it is not satisfied, and as a result, we use condition equation to find out the adjusted values as well as to find out the errors in adjustment computation process. But constraints, irrespective of any error whatever, has to be satisfied. If it is not satisfied, it is not a constraint. That's the difference between condition and the constraint. So let us go ahead and take few more examples of condition equation method. I can give you some homework here. For example, you have situation like that where you measure angle alpha maybe n number of time, alpha 2 and alpha 3. So I have a condition equation here, alpha 3 equals to alpha 1 plus alpha 2. I can also write here alpha 3 bar, that is ideal condition, adjusted condition. And here if I write, let us say V alpha 3 equals to V alpha 1 plus alpha 1 bar, that is the measured value here, these values in the field, and then we have V alpha 2 plus alpha 2 bar here. Can I construct equation Bv plus W here? Let us look into this thing. I can write here, let us say V alpha 3 minus V alpha 1 minus V alpha 2 plus alpha 3 bar minus alpha 1 bar minus alpha 2 bar equal to 0. So this is V, and I can write it here minus 1 plus 1 V alpha 1 V alpha 2 V alpha 3 plus W matrix, which is alpha 3 bar minus alpha 2 bar minus alpha 1 bar 0. So this becomes capital W, this is V matrix, this is B matrix. Again you can find out the solution of V matrix, and then you can find out the rest of the values. Okay, let us take some other examples. Station condition. What is station condition? Let us say at a given station I am measuring 5 angles, theta 1, theta 2, theta 3, theta 4, theta 5. I can write a condition like this, theta 1 plus theta 2 plus theta 3 plus theta 4 plus theta 5 equal to 360 degree, and what we call as station condition. I can also follow the same process. That means I can write here theta 1 bar plus V theta 1 plus theta 2 bar plus V theta 2 plus theta 3 bar plus V theta 3 plus theta 4 bar plus V theta 4 plus theta 5 bar plus V theta 5 equals to 360 degree, because these are the measurements with some errors and so on. Find out what is B matrix, what is V matrix, what is W matrix, and then you are done. On the similar line, you can solve many such examples. Other examples could be, let us say, figure condition. I have this figure of closed polygon where angle theta 1, theta 2, theta 3, theta 4 and theta 5. So I have a condition here that theta 1 plus theta 2 plus theta 3 plus theta 4 plus theta 5 should be equal to 2n minus 4, that is 5 minus 4 divided by 2 into pi, or it is nothing but 180 degree. So the sum of the internal angles should be equal to this value for this pentagon. Same condition equation method will go, and you will find out V theta 2, V theta 3, V theta 4, V theta 5 and so on. This matrix will be of V matrix. Similarly, you can find out other examples. Let us see what are the other examples. Level net problem here. This is the figure condition. What is level net problem? I have level net where, let us say, this one point h1, it has some height h2, this point has height h3, this is h4, and let us say this is h5 here, and we have h6 here. Now you write different conditions here which are independent, and then you do a level net problem analysis. You will write multiple conditions. For example, what do you mean by multiple condition? I will give you another example here, simple one. Let us say there are some angles like this. First is alpha 1, second is alpha 2, third is alpha 3. Now I measure the combined angle here, alpha 4 here, and this angle is alpha 5 here. So I observe all the 5 angles in the field. Now I want to find the adjusted values of these 3 fundamental variables, alpha 1, alpha 2, alpha 3. So I can write here that alpha 1 plus alpha 4 should be equal to alpha 2 here, should be equal to alpha 4, and similarly I can write another condition, say alpha 2 plus alpha 3 should be equal to alpha 5. So these are 2 independent conditions here, because all other conditions can be derived by these 2 equations. Same way for this level net also you will write independent conditions, and once you consider all the dependent conditions, introduce the errors in all the variables like h1, h2, h3, h4, h5, h6 like v1, v2 to v6, and write BV plus W matrix and try to solve. So let us take this example. So here I have 2 functions, let us say f1 LA equal to 0. Similarly here I have f2 LA equal to 0. So what does it mean? If I write here alpha 1 bar plus error in alpha 1 plus alpha 2 bar plus in error here equal to alpha 4 bar plus error in alpha 4. Similarly, I can write another equation from here, it is alpha 2 bar plus V alpha 2, here alpha 3 bar plus V alpha 3 equal to alpha 5 bar plus V alpha 5. I will have 2 equations. How can I write it? Let us see. If I bring all in one side, then I can write here like this, alpha 1 plus alpha 2 minus bar minus alpha 5 bar, that is one thing, plus I can write here V alpha 1 plus V alpha 2 minus V alpha 5, right, equals to 0 here. Similarly, I can write alpha 2 plus alpha 3 bar minus alpha, it should be 4 here and it should be 4 here. It should be 5 here plus V alpha 2 plus V alpha 3 minus V alpha 5, and I can write it 0. I can write this thing in a matrix form. The first one I am writing 1, 1, and then we do not have the alpha 3 here, so I will put 0 here. I have alpha 4 here, then no alpha 5. So this is the matrix here. In this second equation, V alpha 2, no alpha 1, 1, alpha 3, 1, here 0 and minus 1. I can write this way, V alpha 1, V alpha 2, V alpha 3, V alpha 4 and V alpha 5, plus I can write here alpha 1 bar plus alpha 2 bar minus alpha 4 bar, here alpha 2 bar plus alpha 3 bar minus alpha 5 bar. So this is W matrix, this is V matrix, this is B matrix. So I have got the form BV plus W equals to 0. So this is what condition equation method is. Let us take the last one, how to solve the nonlinear problem, or we can take it in a simple way where I can say that B matrix is also given by, here in this main equation I can write this thing, dou f by dou f1 at LA do alpha 3, do alpha 4, LA here, and do alpha 5. Here I can write do F2 LA, do alpha 1, do F2 LA by do L2 here, do F2 LA here, do alpha 3, do F2 LA over do alpha 4, and the last factor is do alpha 5. This is B matrix. What is F1 LA? F1 LA is nothing but alpha 1 plus alpha 2 minus alpha 5 equals to 0, and F2 LA is nothing but alpha 2 plus alpha 3 minus alpha 5 equal to 0. It should be 4, like this. So these are two equations. I am writing B matrix. So that is the way we handle the nonlinear problems. Okay. Now let us take the quality of parameters in condition equation method and observables. Okay. So how to give the quality here? First of all, QVV, which is given like this: P inverse weight matrix BT, M inverse B P inverse. What about the QLALA? That means the quality of the adjusted parameters is given by P inverse minus P inverse BT, M inverse B P inverse is nothing but equal to, if you remember, sigma LA divided by sigma 0 square. What about QLB? We already observe it in the field, so I know it, which is equal to, let us say, P inverse equal to sigma LB divided by sigma 0 square. Okay. Again, I can prove here that sigma VB is equal to sigma LB minus sigma LA. That means adjusted parameter will have higher quality compared to the observed value of variables in the field. Okay. Here we can finish the condition equation method, and let me tell you little more about that. There are some situations where we cannot use condition equation or observation equation method. What could be possibility here? Let us take some example before we finish this lecture. Let us say that you observe a chimney which is like this, and here on this level you observe some points on the surface of the chimney like this. These points should fall on the circle, but because of the error in the measurement that you perform using total station, it will never be a circle. So what will you do? You will find out some points like this. You will try to fit a circle through these points like this to find out what is the exact diameter of the chimney. So now let us see, this center is x0, y0 of circle. Okay. Now these are the observed points. Each point I can say here, let us see xi, yi, and so I can write an equation of circle here: xi minus x0 square plus yi minus y0 whole square minus r square equals to 0 here. Now in this situation, can you use condition equation method? No, because I am observing only x and y. So I do not have a condition where I am observing each and every variable. No, there are unknowns which are x0, y0 and r. They are unknowns, or I can say parameters. On the other hand, can you use observation equation method? Okay. In observation equation method, remember, I should mention the dependent variable explicitly in the form of independent variable, but here I am observing xi and yi. You can argue that I can write y I is equal to plus minus, I can write this way. But one of you may argue that why can't I write xi equals to x0 plus minus r square minus yi minus y0 square. What I am saying here is, it is very difficult to say who is dependent and who is independent among x and y, which I observe in the field. Moreover, when I observe x and y using total station or any other device, they are coming as a couple, right? And they are coming by one device, and I cannot say which is dependent and which is independent. In such a situation, generic form will be BV plus A delta x, or maybe x plus W equal to 0. In such a problem, I cannot use explicitly observation equation method or condition equation method, because both are not applicable. In that case, I use the combined method. So, in the next lecture, we are first going to discuss about the combined method, and then we will see how to conclude all this our knowledge that we have gained in these 4 lectures so far. Thank you very much for patiently listening, and I request you to practice some of the problems that I shared with you. So, once you learn all this thing, you yourself will become more confident, and if you can learn the Python, then you can also do your small work on the complicated problem where you have enormous data that you want to handle. Thank you once again. Thank you very much.